Hello students. Topic of today's lecture is frequency response in case of differential amplifiers. So we are going to cover these issues. First we will discuss the basic points about the frequency response. After that we will cover Miller theorem. So it's very useful tool in simplification of AC analysis of electronic circuits. After that we will use these theories to find out the frequency response of differential amplifier with current source as a load. For this, first we will draw the high frequency equivalent circuit of this particular configuration of amplifier. We will find out its 3 decibel frequency and gain bandwidth product, and then we will repeat all this analysis for differential amplifiers with current mirrored load, and at the end we will summarize our discussion. So first we will talk about the frequency response. So in case of amplifier circuits, the frequency response look something like this. So in the mid frequency range, which is between this lower cutoff frequency to higher cutoff frequency, the gain of amplifier is almost constant, and once we go beyond this range at higher frequency, this gain decreases, and in the same way at lower frequencies, means at frequencies below this lower cutoff frequency, gain decreases. So in both these regions, at low frequency as well as in case of high frequency, this decrease in gain is because of capacitive effects. But these capacitive effects are different in case of different regions. For example, at lower frequency, the capacitive effect is because of the coupling capacitors which are present into circuit and bypass capacitors, right? So these capacitive components are external to the device. They are part of circuit, but they are not within the device. But if we go to this higher frequency range, here this decrease in the gain is because of the capacitive effects which are internal to the devices. They are present in both MOSFET and BJT devices, but in the present discussion we are more concerned about the MOSFET devices, right? Now in case of amplifier design, our main aim is always to have this voltage gain as high as possible, and this bandwidth of the amplifier should also be as high as possible, right? Bandwidth means difference between these two frequencies, that is higher cutoff frequency and lower cutoff frequency. This part is bandwidth, right? So these two performance parameters, the high gain and high bandwidth, they are included in a single performance parameter, and that is gain bandwidth product. It's very important performance parameter because it takes care of the gain of amplifier as well as bandwidth, and our target is to have as high as possible gain bandwidth product. Now this case is true if we are using RC coupled amplifier, but sometimes we use direct coupled amplifiers. For example, the differential amplifier case, which we are going to cover in this present discussion, those differential amplifiers utilize direct coupling, and direct coupling and there are no bypass capacitors. So in that case we will not feel this kind of decrease in the gain at low frequencies. So you can see here, so this is one example of frequency response in case of differential amplifiers, which are direct coupled amplifiers, that starting from the 0 frequency, gain is constant up to this particular value of frequency, and beyond this the gain start decreasing as it was decreasing in case of high frequency in this particular case, right? So in case of differential amplifier or in case of any direct coupled amplifier, we are concerned about this 3 decibel frequency, and this is our bandwidth actually, because starting from 0 to this frequency, gain remains constant, right? And the decrease in gain starts beyond this cutoff frequency. Now another important concept which we must understand while understanding the frequency response of any circuit is the concept of poles and zeros. You see, most of the time we see that the gain of any system, or especially amplifiers, decreases like this. So it decreases like this with frequency. Now you see, so in this range this gain is constant, but at this particular frequency its behavior is changing. Again at this it is further changing, and at this corner it is again changing. So these are the corner frequencies at which we feel certain changes in the behavior of the frequency response. So these frequencies are known as corner frequencies. But some frequencies, they are mentioned like this one and this one, right? These two are mentioned as a pole frequency, because you see here this subscript P, and this frequency is known as zero frequency. So what is the meaning of pole frequency and zero frequency? It is clear here, right? So pole frequency corresponds to corner frequency. This is this corner frequency and this corner frequency, at which slope of the magnitude curve decreases by 20 decibel per decade. You can see here. So in this portion, this slope is almost like it's constant graph. So its slope is about 0 decibel per decade, because there is no change in the gain. But once we come to this corner, now you see the gain is changing by minus 20 decibel per decade. And here, if we reach here, after this again there is minus 40 decibel per decade. So when we are moving from this side to this side, there is decrease by 20 decibel, and from here to here we are going, again there is decrease of 20 decibel. So that's why we call these corner frequencies as pole frequency, because the gain is reducing by 20 decibel per decade. But at this point, you see here, this gain earlier was minus 40 decibel per decade, but now it is minus 20 decibel per decade. So there is an increase by 20 decibel per decade. So this particular corner frequency, at which this slope increases by 20 decibel. So this kind of corner is indicated as zero frequency, right? So it is indicated here by this Z, right? But when we solve a circuit for its a frequency response in the solution, and in that equation we will find this parameter, this pole, this kind of pole, and maybe some zeros also. But we are not interested in all the poles and zeros. We are interested only on the first corner frequency, right? Because once we cross this corner frequency, the gain starts decreasing, and in case of amplifiers, we are no more interested in this area. We are interested only in that area, that portion of the frequency which is below this first corner frequency, right? And the next corner frequency, doesn't matter whether they are pole or zero, we will ignore them. Now, after covering these basic points about the frequency response, now we will go to the Miller theorem. So first we must understand what kind of help is offered to our analysis by this Miller theorem. So for that, first we have to understand what kind of issues we face, what kind of problems we face in handling the capacitive values. Now you see, suppose this is an amplifier having gain A, we have input voltage here, and at the output we have output voltage, and this output voltage is gain multiplied by the input voltage. But for the frequency response, or for the frequency based analysis of the circuit, we must include the capacitive components, and the major capacitive components are connected between the output terminal and ground, and it is indicated at Cout. Another major component is between input terminal and ground, and it is indicated as Cin. Now there is third major component which is connected between output terminal and input terminal, and this capacitive component is known as feedback capacitive component. Now for frequency response, most of the time we try to solve it at the output node, right? And that way we have to include all capacitive components which are connected at output node. So this capacitive component definitely will be included here, and we need to include this capacitive component also, because that is also connected to output node. But problem is the second terminal of this is connected to input node also. So if we have to include this capacitive component into the analysis, then we have to do this AC analysis at both nodes, here and here. So it's not that it is difficult, but it adds some more processing steps, and that way the inclusion of this feedback capacitance into our calculation becomes more tricky. So we want to simplify this process, and that help is offered by the Miller theorem. So now we will see what Miller theorem says and how it is useful in our calculations. Now Miller theorem says that if an impedance Z is attached between input terminal and output terminal of an amplifier, then this Z can be replaced with two impedances. One is connected between input and ground, and second one is between output and ground. So see, for example, here this is some system. So this is input side, and here V1 voltage is appearing on the input side, and this is output side. V2 voltage is appearing here, and there are other connections which are going to different parts of circuit. Now this Z impedance is connected between this output node and input node. Now what Miller theorem says that this Z can be replaced by two impedances, one between input and ground and second between output and ground, something like this. So this Z, which was originally between these two nodes, that Z is replaced by these two components. One is Z1 between input node and ground, second one between output node and ground. Now we must understand that how much is dependence of this Z2 on Z, or you can say how much fraction of this Z will go to Z2 and how much will go to the Z1, right? For that we have to understand some equations. So now suppose this impedance is a capacitive impedance, and so the impedance will be given like this. Now the part which is coming between input and ground, Z1 will be given by this. So it depends on A, gain of the amplifier, and Z2 which is connected between output and ground, that is given by this equation. Now since we are saying that it is capacitive component, so instead of looking at this problem as impedance, we can look at the capacitance value also. So the C1 means the capacitive component which is present between input and ground, that will be something like this, okay, and C2 which is connected between output and ground, that will be like this, right? So it depends on gain, and if the gain of amplifier is greater than 1, and that is normally the case, gain is most of the time greater than 1. So if this gain is greater than 1, in that case you can see this term will be almost negligible, and C2 will be mostly equal to C, or you can see that Z2 is almost equal to Z. So if the gain of amplifier is very large as compared to 1, then this Z2 is almost equal to Z, right? So whatever impedance was connected between output node and input node, that will be almost in the same form it will appear between output terminal and ground, provided A is very large than 1, right? If this condition is satisfied, in this case this. Or you can say that if C capacitance is connected here, then this C will appear as it is between this output and input. The C will remain same, right? The C1 will have a different fraction here, but we are not going to focus on that part. Our main focus in the present discussion is only at the output node, because for finding the frequency response we are going to solve the circuit for the output node. Now we understand Miller theorem, and now we will apply this Miller theorem to solve this tricky part of the circuit, right? Now we have to apply Miller theorem here, and the Miller theorem says that this kind of capacitive component which is connected between output node and ground, output node and input node, so that can be assumed in such a way that one part of this is appearing between output and ground, and another part will appear between input and ground. That is, instead of this CF, we can look this circuit and something like this. Now you see, this is CF feedback capacitance, second part, one component is here, and CF feedback capacitance, its one component is appearing between input and ground. Now as I discussed in the earlier slide, if the gain of amplifier is greater than 1, then this component is almost equal to CF. It means we can assume that whatever was the capacitive component connected between output terminal and input terminal, we can assume that it is connected as it is between output node and ground. So this is appearing in parallel with the already existing output capacitance. So the net output capacitance will be sum of these two, because they are appearing in the parallel. So that way the use of Miller theorem have simplified our problem, because now we need to do entire analysis only at the output node. We need not to go to the input node side, right? Now we will apply this concept to our discussion. So now we will go to this frequency response or frequency analysis of differential amplifier with current source load. First we have to understand what is its high frequency equivalent circuit. Now this is the circuit diagram of a differential amplifier with current source as load, and you know that its equivalent circuit is given like this. Now you can see there are two output terminals. One output terminal is here and second output terminal is here. This VO1 corresponds to this VD1, this terminal, and this VO2 second output corresponds to this output, which is shown here in this circuit. Now since this circuit is symmetrical circuit, means if we assume a symmetrical line here, so this left side and right side is exactly same. And from this equivalent circuit also you can see that if we assume a symmetry line here, this left side and this right side, that is exactly same because circuit is symmetrical. So because of this symmetry, what we can do, we can find out its frequency response at one node, right? And whatever result we get, those results will be applicable for the second node also, and that way the result will be applicable to entire differential amplifier. So normally what we have to do, we have to solve it as a single output or single ended output mode, but input is differential input, so differential input and single ended output. That way we have to solve it. This equivalent circuit, or you can say half circuit, we will use to find out either this or this. It means we will solve it either at this node, but on the input side it's differential input signal, or we can solve it at this node. It's our choice. So I prefer that I will use this half part. You can use anyone, it's exactly same. Now here the high frequency equivalent circuit of this part will be given like this. So we have avoided the use of this side because that part we are not going to use in our solution. So we have to solve it at output node, and at output node only these components are connected. It's something like this. Now this R1, so R1 is coming from the parallel combination of these two resistive components. So this R1 is given by this. So it's drain source resistance of first device, and this is drain source resistance of this third device. So RO1, RO3, right? And this C1 is the total capacitance or total or net capacitive components which are connected between this output terminal and ground. And you can see that we have selected this part. It means output, this output and ground, right? So whatever capacitive components are connected between this terminal and ground, those components will be represented by this C1, and C1 will be given like this. So you can see here in the C1, first component is CGD1. CGD1 is gate drain of first device. This is gate, this is drain. It means we are talking about a capacitive component which is connected between this gate and drain. So this is this CGD1, right? I am mentioning here 1. This is our first component. Now second component is like gate drain of third transistor. This third transistor, so this is drain, this is gate. So the capacitive component which is connected here between this to that component. Now this is output terminal, and this is going to ground. Why? Because when we do AC analysis, then all DC sources are grounded. So this VGG2 is grounded, so this terminal is actually our ground terminal. The second component which is connected here, right? So that is between output terminal and ground. So that component is this one, right? And the third component, drain bulk capacitance of first. So this is drain, and here there is a capacitive component, and this is going to ground, and this is drain bulk capacitance. So this is, I am mentioning a third value. So third component is this, and this is fourth, drain bulk of third, because this third M3, its drain is connected to output, and its bulk is grounded. So this capacitance between drain and bulk, so that is fourth. right? And the fifth is load capacitance. So load capacitance, it is not shown here, but the load capacitance is also connected between this output terminal or ground. So it may be present, it may not be present, but we have included it depending on the situation. Sorry. Now you can see that all these three capacitive components, and even this fourth one, if it is present, all these are between output terminal and ground. Only this capacitive component is between output and input. You can see output and input. And if we look at this equivalent circuit, so that capacitive component is actually present here. So this is your feedback capacitance. So but we are not considering it as if it is connected between output and input. Rather we are considering it as if it is connected between output and ground. And why we are doing it like this? Because of Miller theorem. So this first CGD1, so it is assumed to be part of the C1, that is, we are assuming that it is connected between output and ground, right? And so this is feedback capacitance, which is added here because of Miller theorem. And all these capacitive components are the capacitive components which are already present here between output and ground, right? So now we understand the AC equivalent circuit or high frequency equivalent circuit of a differential amplifier with current source load. Now we will use this equivalent circuit to find out the voltage gain as a function of frequency. So all these things are repeated here. This is high frequency equivalent circuit, and this R1 is given by this parallel combination, and C1 is the sum of these different capacitive components. So now we have to find out the voltage gain here. For that purpose, what we will do, we will apply KCL, Kirchhoff's current law, at the output node, and we can see that no source is connected, so there is no net current. Net current is 0, but all these branches will have current because this is like output voltage here. Now if we apply this Kirchhoff's current law, so it will be something like this. So we are mentioning the current here in this branch is given by this formula, it's already mentioned here. Current here in this branch will be given by the net voltage divided by this resistance, and voltage which is appearing across this resistance is this V0. So V0 divided by R1, and here this current in this branch will be given by V0 divided by capacitive impedance, and the capacitive impedance, you know, it's 1 by SC. So that will come here like this, or you can say it's admittance multiplied by this voltage across this terminal. So that will give us current here in the capacitive branch. The net current is 0, right? And in this equation you can see that this part is differential input voltage, and this is output voltage, this is output voltage, and all other components which are present here, they are all constant. C1, R1 and GM1, all these are constant. So we can do some mathematical manipulation, and we can separate out V0, and we can divide V0 by VID. So that way we can find out the ratio of output voltage to input voltage, and you can see that it's mentioned as single-ended differential output voltage, right? Sorry, single-ended output divided by differential input voltage. And after all this mathematical manipulation and by putting some constant there, so we will get this kind of result, right? This transfer function. Now this, if this S is equal to minus omega 1, so what will happen? So if it happens, in that case this voltage gain will be infinite, because this S plus omega 1 is appearing in the denominator. So infinite gain is not possible, but actually what happens, so here if this is W or omega and this is A, so and the gain will be something like this. So what happens at this particular thing, that when this S is equal to omega 1, or you can say at this omega 1, so we get first corner frequency, and here this is only one corner frequency. So this omega 1, this is your cutoff frequency, and beyond that the gain keep on decreasing, and before this the gain is almost constant like this. So this is your 3 decibel frequency. So this omega 1 is actually given by this formula, and this AVDS, that is this gain, this part, this gain, voltage gain, that is GM into R1, and this omega 1 is 1 by R1 C1. Right now here this 3 decibel frequency is given in terms of resistance, net resistance between output terminal and ground, and net capacitance between output terminal and ground. Sometimes it is preferred to use conductances instead of resistances. So if we prefer conductances, then instead of writing net resistance, we have to write net conductance between this output terminal and ground, and net conductance is inverse of this resistance. So net conductance is given by this. So we have to add conductance of this device, output conductance of this device, plus output conductance of this device. That way we will get the net conductance here, right, divided by C1. C1 is the capacitive component, net capacitive component between output terminal and ground. So that way we can find out the upper cutoff frequency. Now the next important performance parameter in case of any amplifier is its gain bandwidth product. So the gain bandwidth product, you can see that for that first we need to find out voltage gain, and the cutoff frequency we already know. So voltage gain, we already know that the differential voltage gain of this differential amplifier with current source as a load is given by this formula, and its cutoff frequency is given by this formula, where R1 is this one, right. Now if we want to find out gain bandwidth product, this GB gain bandwidth product, that will be given by product of this voltage gain which is coming from here and this cutoff frequency which is coming from here. Now you can see that this parallel combination of resistance is actually equal to R1. So the R1 will cancel this parallel combination. So what is left behind is transconductance of this first device divided by this C1. So that is gain bandwidth product. Now we have completed our frequency response related discussion in case of differential amplifier with current source load. Now we will move to the second kind of circuit, where differential amplifier with current mirror load is considered. And in this case also we will repeat exactly same steps. First we have to find out the high frequency equivalent circuit, and then we will find out 3 decibel frequency and gain bandwidth product. So you already know the circuit of current mirror based load in case of differential amplifier. This circuit look like this, and you already have some idea about its equivalent circuit. But remember, this case is not like the case of current source as load. Here there is no symmetry. If you assume a symmetry line here, and you see on the left side and right side, circuit is not exactly symmetrical. Here this drain is connected to gate, but here there is no such connection is there, right. So in the same way, if you see here at the equivalent circuit, that symmetry doesn't exist. So here there are 3 resistive components and 1 current source, but here there are 2 components and 2 different current sources are there. And you know, this output in this case of current mirror load is a single-ended output. So we need to solve it for this node, because this is our output. But since this is output, but don't think that we can ignore this left side, because you know that in case of this right side, there are certain sections where the current, for example this particular section, the current in this section depends on VG3, means this voltage. So if you want to solve this part, right side part, we need to solve this one also, because if we solve, only then we will be able to find out voltage here, and that voltage will be used to find out the current in this component, and only then we will be able to find out the voltage, right. So we cannot omit any part here, right, left side, right side, both we have to include. But yeah, we can ignore this part, because that input side is not going to be used in the frequency response solution. Only output terminals we need to solve. So the equivalent circuit, high frequency equivalent circuit means the circuit which takes into account the capacitive components also. That circuit will be something like this. So here this is this left side, you can see here this current source, and this R1 is the parallel combination of these three resistive components which are present here. And in addition to these resistive components, we have assumed that there is a capacitive component between this output terminal and ground. This output terminal means we are talking about this output, but this output is not our final output. Our final output is on this side, right? So now we have seen the high frequency model of this left side. Now we go to right side. So right side, in this diagram there are certain changes. Actually there is nothing is changing, so it's exactly same. Only thing is that some components are rearranged. So this output node which was indicated this side, now it is indicated towards this side, because normally it is our habit that we look at things from left to right. So whenever we write from left to right. So that's why this output is shown towards the right side. Otherwise there is no difference between this and this. Only difference is that we have added capacitive components here. Okay, so this side, if we see this current here, this current source here, and this resistive component, they are together represented by this R2, and we have assumed one capacitive component which is between output terminal and ground. So that is indicated here towards this side, and our final output is here V0. Now, so this R1 is the parallel combination of these three resistive components. So it is shown here, and it is approximately equal to 1 by GM3, because this GM3 is very large. So 1 by GM3 is very small as compared to this. So in a parallel combination, the smallest resistive part dominates. So this R1 will be given mainly by 1 by GM3, and here this R2 is parallel combination of these two resistive components. It is written like this. Now if we talk about the C1 and C2, now all the capacitive components which are connected here, you can see yourself, and now you are smart enough, you already know that how we have included these capacitive components here. In the earlier circuit also you have seen it. So we can write this expression for C1. So all the capacitive components which are connected between this node and ground, means this node and ground, they are included in C1. And in the same way we can write expression for C2, and C2, you see, it includes CL also, because this is our final output, and final output means this side, and here the CL is also included, right? And you can see again in both these expressions there is CGD1 here, gate drain capacitance. It means this gate drain capacitance, and this capacitance is between output terminal and input terminal. So that way it is like a feedback capacitance. And this side also, this is feedback capacitance. But these feedback capacitances are included in C1 and C2 because of Miller theorem, right? Now we move to the next part. Now we know this equivalent circuit, high frequency equivalent circuit, and all these relevant expressions are given here. Now first we are writing expression for V1. The V1 voltage here is this current multiplied by the net admittance, inverse of admittance, or net impedance of this part. Net impedance of this part is inverse of admittance, and the admittance of this sections is given here. This GM3 is the admittance offered by this part, and SC is admittance offered by this section. So V1 we know, and this V1 will be used to find out the net current in this side. And the current here is I0 is a combination of these two current sources. So this part gives current in this branch, and this component gives current here in this branch. And for this current we have to use value of V1, and V1 will come from here. Now this output voltage which is connected here, which is between this terminal and this terminal, if you want to find out this output voltage, that output voltage is the current, net current multiplied by the net impedance offered by this section. So net impedance is the parallel combination of these two. This is impedance offered by this resistive component, and this is offered by this capacitive component, and it's multiplied by current, net current, which is flowing here. So if we put this value of I naught here, but before that remember we have to put value of V1 from here to here also. So we will get this expression something like this, and we can further simplify this, and we will get this equation of voltage gain like this. For this, finding this voltage gain, it's V0 divided by differential input voltage. So this VID will cancel from here, and this expression is something like this. Here you can see there are two frequency component or corner frequencies, omega 2 and omega 1, and this omega 2 is this and omega 1 is this. So normally what happens, so I told you before also, so if we have this kind of frequency dependent behavior, something like this, ignore this part, it's the mistake, right? So if you see this kind of thing, then you may get two corner frequencies, one here and one here, right? But this second one is at higher frequency, we can ignore it, because at this corner frequency itself gain started decreasing, and the next frequencies we can ignore. So which one is to be ignored, that we have to see. The higher one we have going to ignore. So but if you see the R2 and C2 and R1 and C1, R2 and C2 is large because you can see here this R1 is parallel combination of this and this. So R2 is this part. So R1 means it's almost R2 in parallel with this component. So that's why R1 is smaller than R2. And in the same way you can see that C2 is large because C2 includes this load capacitance also. So the R2 C2 is large, and that's why omega 2 is smaller. It means the omega 2 is here, and this one is omega 1. It means this omega 1 we need not to consider, because already the gain started falling. So we are interested only in this, because it indicates this, that 3 decibel gain, the gain already have reduced by 3 decibel gain. So this one is the main deciding factor. Now this omega 2 dominates, and that here you can see this cutoff frequency is mentioned in terms of this resistive component. So sometime instead of resistive component, it's better to express it in terms of conductance values, and conductance is inverse of resistance. So net conductance will be here in the numerator. It will be something like this. But sometime we need to find out it for some other parameters also. For example, how much is voltage gain here during this frequency range. For that we need to simplify it further. So if you want to simplify it further, it will be something like this, and you can manipulate, and you can use some abbreviations, and something like this, and this AVDS0, so this voltage gain will be given by this expression, and omega 1 prime is something like this. So that simplification depends on your choice. If you want to go in more detail, you can do it, but from examination point of view, if you limit yourself to finding out omega 2 and omega 1, that also is sufficient. So now we know the cutoff frequency. Its next step is to find out the gain bandwidth product. So first we are writing this expression for the differential voltage gain, and its cutoff frequency is given by this formula, and you know this R2 is this, and it can also be, this cutoff frequency can also be expressed in terms of conductance parameters. So finding gain bandwidth product is very easy now. So just find out the product of voltage gain. So this voltage gain is here, it's coming from this voltage gain expression, and this cutoff frequency is coming from here. But you know this R2 is parallel combination of these two resistances, so this is just R2, it will cancel this R2, and that way gain bandwidth product is given by this expression, right? So now we have to summarize our discussion. So we have covered two kind of differential amplifier. So one was with current source load, and second one was with current mirror as load. In case of current source load, we have seen that high frequency equivalent circuit is given by this diagram, and here this R1 is given by parallel combination of these two resistances, and C1 is given by this expression. So we have seen that its cutoff frequency is given by this formula, and in terms of conductances it can be expressed something like this. Now the gain bandwidth product is given by this parameter. In case of current mirror load, high frequency equivalent circuit is something like this. Here this R1 is given, R2 is given by this. Only those capacitive component, those values I am mentioning here, which are between real output and ground, and the C2 is this combination. It includes load capacitance also if it is present there. So for this we have seen this cutoff frequency in terms of resistance is given by this, and if we want to express this upper cutoff frequency, 3 decibel frequency in terms of conductance values, it is something like this, and gain bandwidth product is given by this. So that way we have covered this topic of frequency response in case of differential amplifier with active load. So if you have any doubt in this whole discussion, so you can discuss with me anytime, and I think it's okay then. Thank you very much. Thank you.